This code demonstrates how to fine-tune a pre-trained MobileNet v2 model using TensorFlow and Keras to perform image classification on a custom dataset. It begins by loading image data from directories, applying resizing and batching. The MobileNet v2 base model is loaded without the top classification layer, and its weights are frozen to retain learned features. A custom classification head is then added, followed by model compilation using the Adam optimizer and sparse categorical cross-entropy loss. The model is trained over several epochs, and training, validation, accuracy, and loss are visualized to evaluate performance. This approach allows efficient training with limited data by leveraging transfer learning. The IDE being used in the screenshot is Visual Studio Code, VS Code. You can recognize it by the distinctive icons in the left sidebar: Explorer, Search, Source Control, Run, Extensions. Dark-themed interface with a top breadcrumb bar showing the notebook file path, cell-based structure indicating a Jupyter notebook, .ipynb running in VS Code. Additionally, the code cell includes Python syntax highlighting, and the interface includes Jupyter-specific options like Run All, Clear All Outputs, and Select Kernel. Let's begin by importing the libraries needed for this deep learning project. The matplotlib.pyplot library is used for creating visualizations like graphs and image displays, which help us understand the data and training results. NumPy is a powerful numerical library that allows us to work with arrays and perform mathematical operations efficiently. The OS module provides functions to interact with the operating system, such as accessing directories and file paths. Lastly, TensorFlow is the core deep learning framework we'll use to build, train, and evaluate our neural network models. Together, these libraries form the foundation for working with datasets, visualizing results, and training machine learning models. This code sets up the dataset for training a machine learning model. First, it defines the target image size as 160 by 160 pixels, which means all images will be resized to this shape for consistency. Then it downloads a zip file named cats and dogs.zip, containing a filtered dataset of cat and dog images. This is done using TensorFlow's utility function getFile, which fetches the dataset from the provided URL and extracts it. The os.path.join and os.path.dirname functions are used to construct a clean file path to the extracted dataset, ensuring it's compatible with the operating system. This prepares the dataset for easy loading and use in training the model. This code loads the training and validation datasets from the local directory where the images were extracted. It uses TensorFlow's image dataset from directory function to read images from the respective folders, train and validation, inside the main dataset path. Both datasets are configured to shuffle the images, shuffle, true, to ensure the model sees a random order of images during training. They also use a batch size of 32, meaning the model will process 32 images at a time during training. Each image is resized to 160 pixels to match the input size expected by the model. This step prepares the image data for training and evaluating the deep learning model. This code checks and prints the version of Python being used in the environment. It starts by importing the built-in sys module, which provides access to system-specific parameters and functions. Then, it uses print to display the current Python version by accessing the version attribute from the sys module. This is useful for verifying compatibility when working with specific libraries or features that depend on a certain version of Python. This code displays a sample of 4 images from the training dataset along with their corresponding labels. It starts by looping through one batch of data from the training dataset using .take1. Inside the batch, it iterates through the first 4 images using a for loop. For each image, a subplot is created in a 2x2 grid layout. The image is displayed using imshow after converting it from a TensorFlow tensor to a NumPy array and ensuring it's in the proper format, uint8. The corresponding class name, e.g., cat or dog, is used as the title of each subplot, and the axis is hidden for a cleaner look. Finally, matplotlib.pyplot.show is called to render the images. This step helps visually inspect if the dataset was loaded correctly. This code builds a transfer learning model using TensorFlow and the pre-trained MobileNet v2 architecture. The base model is loaded without its top classification layer, include, top false, and with weights pre-trained on the ImageNet dataset. The model takes input images of size 160x160 with 3 color channels. To improve generalization, image augmentation is applied using random horizontal flips and rotations. Then, the images are pre-processed to match MobileNet v2's expected input format. The base model is used with training false to keep its weights frozen during initial training. After feature extraction, a global average pooling layer reduces the feature map size, followed by dropout to prevent overfitting. Finally, a dense layer with one output neuron is added for binary classification. For example, cat versus dog, and the complete model is created using the functional API. This code fine-tunes the pre-trained MobileNet v2 model for better performance on the cat and dog classification task. By setting base, model, trainable, true, all layers are made trainable, but the loop freezes the first 100 layers to retain learned features and avoid overfitting. The model is compiled with a binary cross-entropy loss function, suitable for binary classification, and the RMS prop optimizer with a reduced learning rate to ensure stable weight updates. It is then trained using the fit function for 10 epochs on the training dataset, while evaluating its performance on the validation dataset. The training output shows progressive improvement in both training and validation accuracy, reaching over 97% validation accuracy by the 10th epoch, with decreasing loss values, indicating successful learning and good generalization. This code visualizes the model's training and validation accuracy over each epoch using matplotlib. It starts by creating a plot with a figure size of 888 inches. 2 lines are plotted, one for the training accuracy, and another for validation accuracy, val accuracy, both extracted from the history object returned by model.fit. The x-axis is labeled epoch, and the y-axis is labeled accuracy, with the y-axis values limited between 0.5 and 1 to better highlight the changes in performance. A legend is added to distinguish the 2 lines, placed in the lower right corner. Finally, show displays the graph, providing a clear visual summary of how the model learned and improved during training. This graph visually represents how well the model performed during training across 10 epochs by comparing training accuracy, blue line, and validation accuracy, orange line. Each point on the x-axis represents an epoch, one complete pass through the training dataset, while the y-axis shows the accuracy ranging from 0.5 to 1.0. The training accuracy starts lower, around 63%, because the model begins with randomly initialized weights in its newly added layers. As training progresses, the blue line steadily rises, indicating that the model is learning and adjusting its internal parameters to better predict the training data. Small fluctuations in the line are natural and often due to variations in mini-batches. The validation accuracy begins higher than the training accuracy, around 76%, and increases quickly to reach around 98% by the final epoch. This line shows how well the model performs on unseen data, and it is a good measure of how well it generalizes beyond the training set. The fact that validation accuracy stays consistently higher or close to training accuracy without dropping sharply is a strong sign that the model is not overfitting. Overfitting would typically show a wide gap where training accuracy continues to rise while validation accuracy plateaus or decreases. Additionally, the flattening of both curves near the top indicates that the model has nearly converged, meaning further training may yield only minor improvements unless other changes, like learning rate tuning, data augmentation, or more complex architecture, are introduced. You've now seen how to fine-tune a pre-trained model, train it on your own dataset, and visualize the results. The model has learned effectively and generalizes well. This is a great example of how transfer learning, when combined with quality data and careful tuning, can produce powerful results in a short amount of training time. Keep exploring, testing, and visualizing. Every experiment brings you closer to mastering deep learning. Happy coding!